Hey everyone! Today we're going to learn how to multiply polynomials using a generic rectangle. Now let's say that you're in charge of hosting a large event for a lot of people. So you rented out a venue space and you want to figure out if there's enough chairs for the number of people that you invited. So here's an example of a seating arrangement or a diagram. Okay, now go ahead and count the number of chairs. I'll give you some time. Okay, so it turns out that there are a total of 44 chairs. Is that what you guys got? Now, what strategy did you use? Did you count each chair one by one? Or is there a faster way of counting the number of chairs? Well, one way to do this is to find the total number of rows times the number of columns. Now for this seating diagram, there are a total of 4 rows and 11 columns. So if you multiply 4 by 11, you get a grand total of 44 chairs. Now that was pretty simple, but here's another example of a seating diagram, but this time we need aisles. Now we need aisles for people to walk through. So notice in this seating diagram, we have 4 sections because we have 2 aisles. Okay, now I'll give you guys a moment to calculate the total number of chairs for this seating diagram. Okay, so it turns out for this seating diagram, there are a total of 40 chairs. Is that what you guys got? Now, what strategy did you use to calculate the total number of chairs? Now, one strategy is to find the total number of chairs for each of the 4 sections and add them all up. So for the first section, we see that there are 3 rows and 3 columns. So there's a total of 9 chairs. Now the second section, we see 3 rows and 5 columns, so there are a total of 15 chairs. Now for the next column, we see 2 rows and 3 columns, so we see 6 chairs. And then lastly, for the last section, we see 2 rows and 5 columns, so that gives us 10 chairs. So if we add up the total number of chairs for each of the 4 sections, we get 9 plus 15 plus 6 plus 10, and that gives us 40 chairs. However, is there a faster way to figure out the total number of chairs? Yes. If we disregard the aisles for just a moment, we can see that we can find the total number of rows and multiply that by the total number of columns. So, how many rows do we have? We have 2 rows plus 3 extra rows. That gives us a total of 5 rows. We are going to multiply that by the total number of columns. In this diagram, we see 3 columns plus 5 more. So that gives us a total of 8 columns. So now the total number of chairs must be 5 times 8, which gives us again 40 total chairs. So when we multiply 2 polynomials, we're going to be essentially doing the exact same thing. This time, we're going to be using something called a generic rectangle or an area model. So with our similar chair diagram that we had before, let's pretend instead of rows and columns and chairs, we're going to see it as 2 feet plus 3 feet in length. And for the width of the rectangle, we have 3 feet and 5 feet in width. So when we multiply those two, we see 5 feet times 8 feet, which gives us 40 square feet. Notice there's actually 40 square feet in this entire rectangle. You can count them out. There's actually 40 of them total. The other way to find the total area is again multiplying each of the length and width of each of the 4 sections and then add them all together. So for the first rectangle, we see 9 square feet. Then we got 15 square feet. Then we got 6 square feet. And then lastly, we got 10 square feet. So if we add them all together, we again get 40 square feet. So area can be represented in two different ways. The area can be represented as a sum, which means that you can add up the areas for each individual pieces or sections. But area can also be represented as a product of total length times total width. Okay, so now we're ready to multiply two polynomials. Here's an example. This is multiplying a binomial times another binomial. Now, does this expression appear to look like area as a sum or area as a product? For this expression, it appears that we wrote the area as a product of length times width. So when we multiply two binomials, what we're essentially finding is the area as a sum. We're going to find the area of each individual sections, just like our previous examples, and add them all together. Remember, the area can be written in two ways: area as a product and then area as a sum. So what is the area as a sum? Let's go ahead and draw a rectangle to represent this situation. This is an example of a generic rectangle. Now, a generic rectangle can be written with a length of x plus 2 times a width of x plus 3. The length is x feet long plus 2 more. Now that appears to have divided the rectangle into two sections. Now what about the width? The width of the rectangle is x plus 3. So it's x feet wide plus 3 more, which again divides the rectangle into two more sections. Now, how many sections do you see? There's a grand total of 1, 2, 3, 4 sections of this rectangle. So to write the area as a sum, what we're going to do is to find the area of each individual sections and then add them all up. Okay, so what's the area of this first section? This rectangle has the length of x feet long times the width of x feet wide, x times x, which can be written as x squared. Now what about this section of the rectangle? The area of this rectangle is x feet long, the length, times 3 feet wide. So x times 3 can be written as just 3x. What about this section of the rectangle? This section of the rectangle has 2 feet long, the length of 2, times x feet wide. So 2 times x is just 2x. Lastly, what about this last section of the rectangle? We have 2 feet long, the length of 2, and 3 feet wide. So the area of this section of the rectangle is 2 times 3, which is 6. Okay, so now that we're ready to find the area as a sum. The area as a sum is to add up the area of each individual section and put them all together. So we have x squared plus 3x plus 2x plus 6. X squared plus 3x plus 2x plus 6. And that is the area as a sum. But is there a better way to write that? Can we simplify something? Yes, in fact, 3x and 2x are like terms. So if you were to combine these two together, we have 5x. So the area as a sum is x squared plus 5x plus 6. Okay, now I think we're ready to do some more examples of multiplying two polynomials. Okay, so here's another example of multiplying two polynomials. Now this is written as area as a product. So we want to find the area as a sum. So let's go ahead and draw another generic rectangle. We have a rectangle with the length of 2x plus 3 times the width of x plus 4. So the length is 2x feet long plus 3 more times the width of x feet wide plus 4 more feet wide. So again, this looks like it's divided into 4 sections because the length is divided into 2 sections times the width, which is also divided into 2 sections. Okay, so now to write the area as a sum, all we gotta do is find the area of each individual sections and add them all together. Let's go ahead and do that. For the first rectangle we see here, we see 2x feet long, the length of 2x, times the width of x. That is 2x times x. If you simplify that, that is 2x times x is x squared. The area of that first section is 2x squared. Now what about this section of the rectangle? This section has the length of 2x times the width of 4. So 2x times 4 gives us 8x. What about this section of the rectangle? This section has the length of 3 times the width of x. So 3 times x is just 3x. And lastly, what about the last section of the rectangle? This section has the length of 3 feet long times 4 feet wide. 3 times 4 just gives us 12 square feet. So now what's the area as a sum? We have 2x squared plus 8x plus 3x plus 12. But can we simplify this expression? Yes. Notice that the 8x and the 3x are like terms. So when we combine these two together, we essentially have 11x. So what's the grand total? We see the area of the sum is 2x squared plus 11x plus 12. Now let's try some harder examples. Okay, so here's an example of multiplying two polynomials. So again, we have the area written as a product, and we want to find the area written as a sum. So let's go ahead and draw a generic rectangle again. We have length of 3x minus 3. Don't forget the minus sign because it's minus 3 this time. Now we also have the width of 2x plus 5. Now again, this divides the rectangle into 4 sections because 3x minus 3 are 2 terms, so it divides the rectangle into 2 sections. 2x plus 5 is again 2 terms, so we're going to divide the rectangle into 2 sections again, giving us a grand total of 4 sections. So now let's go ahead and find the area of each section and add them all together. So for the first section of the rectangle, we see the length of 3x times the width of 2x. 3x times 2x, well, 3x times 2x, well 3 times 2 is 6, but x times x is x squared. So we have 6x squared. Now what about this section of the rectangle? The length is 3x times the width of 5. So 3x times 5 just gives us 15x. Now what about this section of the rectangle? We see this length to be negative 3 times the width of 2x. So negative 3 times 2x is negative 6x. Now what about this section of the rectangle? We have negative 3 feet long and then 5 feet wide. So negative 3 times 5 is negative 15. So that gives us a grand total of 6x squared plus 15x minus 6x minus 15. But again, is there something that we can simplify? Yes, the 15x and the minus 6x are like terms. So this gives us 6x squared, and then 15 minus 6 is just 9x minus 15. Now let's try one more harder example. Okay, so here's our last example. This is again written as a product of length times width. So let's go ahead and draw a generic rectangle. Okay, now the length is 2x minus 3. That divides the rectangle into two sections. But what about the width? The width is x squared plus 2x minus 5. So this divides the rectangle into three sections. So we're going to draw two lines. Now we have 6 total sections because 2 sections multiplied by 3 more sections, we have a total of 6. So what's the area of each individual parts? So this area is 2x times the width of x squared. 2x times x squared, that is 2, and then x times x squared, that's x to the third power. Because x times another x, because it's squared, x times x again, is x to the third power. Now what about this section? This section of the rectangle can be multiplied by the length of 2x times another 2x. So 2x times 2x, that gives us 4, and then x times x again is x squared. What about this section of the rectangle? This section of the rectangle has a length of 2x again times a width of -5. So 2x times -5 gives us a negative 10x. Okay, now what about this rectangle? That rectangle has a length of -3 times the width of x squared. So -3 times x squared is just -3x squared. What about this rectangle? This rectangle has a length of -3 times 2x. So that gives us -3 times 2x, which is -6x. And lastly, what about this section of the rectangle? That section of the rectangle has -3 as our length and -5 as the width. -3 times -5, when you multiply two negatives, gives us a positive 15. So let's go ahead and add them all together. We have 2x to the third power plus 4x squared minus 10x. But don't forget the minus 3x squared, the minus 6x, and the plus 15. So when we put them all together, what do we have? Is there something that we can combine? Are there any like terms? Yes. The 4x squared and the minus 3x squared combines. These two combine to be just 1x squared. Now, is there anything else that combines? Yes. That negative 10x also can combine with negative 6x. These two to combine to be negative 16x. So what's our grand total? What's our area written as a sum? 2x to the third power. Now these two to combine, 4x squared minus 3x squared, is just 1x squared. Now negative 10x minus 6x is negative 16x. And lastly, plus 15. And there you go.